Welcome to our lecture online. The next problem will probably take a little bit more than the 3 minutes to figure out. It deals with the mass defect and nuclear decay. So let's read the problem. It says a heavy nucleus N at rest undergoes fission where N becomes P plus Q, where P and Q are two lighter nuclei. Let delta equals the mass of N minus the mass of P minus the mass of Q, essentially the leftover mass or the mass defect, where m sub n, m sub p, and m sub q are the masses of n, p, and q respectively. EP and EQ are the kinetic energies of p and q respectively, and the speeds of p and q are vp and vq. If c is the speed of light, which of the following statement or statements are correct? So there's 4 possible statements. Let's see which of those may be correct. So A seems to be fairly straightforward, because remember what Einstein said, that energy is equal to mass times c squared. So in this case, the mass is going to be the mass defect, the leftover mass from the nuclear reaction. So in this case, we can say that energy is equal to the mass defect times c squared, which is what we have over here, and they claim that this is equal to the sum of the two kinetic energies, which we can assume that all the energy goes into moving the two particles that were created to two lighter nuclei. So it seems reasonable to assume that the total energy of the two particles combined add up to mc squared. So that's essentially what that is. All right. The next one I want to tackle is C, because that looks fairly straightforward. We can use the conservation of momentum. Remember that the particle starts at rest, breaks up into two, and they both move off, presumably in opposite directions. So we can say by using the conservation of momentum that P initial equals P final. That means that 0 for the initial momentum is equal to the mass of particle P times the velocity of P minus the mass of particle Q times the velocity of Q, assuming of course that they will be moving in opposite velocities. So if I then write them as follows, I can write that mp/vp is equal to mq/vq, and then if I write all the v's on one side, I can write that vp over vq is equal to mq over mv, which is not v but p, yep, wrong letter, which is exactly what I see over here. So I can see that C is correct as well. All right, now for the 2 more difficult ones, B and D. What about B? Can we just kind of look at that and say if that's true or not? Well, notice what they're claiming here, that the energy is equal to the ratio of the mass of the particle divided by the total mass. So as a fraction of the total mass, but that wouldn't be the case, because remember that kinetic energy, by definition, is equal to 1/2 times the mass times velocity squared. And notice if the mass is smaller, then the velocity will probably be bigger because of this relationship right here. So I would say that B cannot be correct, because it's simply not a result of their respective masses, but also of their velocities. So I'd say B would not be a good choice. How about D? The magnitude of momentum for P as well as Q is equal to that. Wow. Where do we begin? Well, let's see here. We do have this equation right here. We also have the energy equation. And maybe we'll start with that one. Maybe I'll come over here, and we can say that energy of P plus energy of Q must equal, like we said, c squared times delta. And energy of P would be 1/2 the mass of P times the velocity of P squared plus 1/2 the mass of Q times velocity of Q squared, and that should equal c squared times delta. If I now multiply everything by 2 to get rid of the 1/2, and I have m sub p v sub p squared plus m sub q v sub q squared is equal to 2c squared delta. And notice I have a 2c delta, and if I square this, I get a 2c squared delta. It looks like I'm in the right ballpark, but not ready to make a decision yet. If I now multiply this one by mp, make it mp squared, and divide by mp, and I multiply this one by mq, so it becomes mq squared and divide by mq. Nothing has changed, it's still equal to 2c squared delta, but now notice in the numerator I have the momentum of p squared, and here I have the momentum of q squared, and we already know that the momentum by definition must be equal to each other. So I can replace this by the momentum of p squared, and so what I have now is, if I come over here and continue, I have mp squared vp squared over mp plus, that becomes mp squared vp squared, because the momentum must be the same, so divided by mq is equal to 2c squared delta. So now I can factor out an mp vp squared. So I can write this as mp squared vp squared times 1 over mp plus 1 over mq, and that equals 2c squared delta. Now what I can do is I can add these up, so this can become the product over the sum, because what I have here is I have mp squared vp squared times, the common denominator is going to be the product, so I have mq plus mp over the product, mq is equal to 2c squared delta, and then moving that to the other side, I can now take and the square root of both sides. I can say mp vp is equal to the square root of 2c squared delta times the inverse of that, which is mp mq divided by mq plus mp, like this. And now notice that's the momentum of one particle, which is the same as the momentum of the other particle. I do have the square root of 2c squared d. Now the c can come out, right? I could write this as c times 2 delta times this quantity, which is exactly what I have over here. Mu is equal to this quantity right there. And notice I have the exact thing that I need to show that D is correct as well. So it turns out that 3 of the 4 statements in this case are correct. B doesn't seem to be correct because of the relationship between kinetic energy, mass, and velocity. And so that's how we determine those 3 answers are the ones that will give you the full credit on this problem. And again, I don't think I got it done in less than 3 minutes. So the challenge on time is always there in this test.